So in this video we're going to talk about the uniform limit theorem, which is our first example of the use of the stronger notion of convergence that is uniform convergence. So let's begin then with a statement of the uniform limit theorem. So this theorem is about sequences of functions that converge uniformly to the limit function, and it's about the situation where all of the functions in the sequence are continuous over the domain, and then you can conclude that the limit function is also continuous over the entire domain, provided that the sequence of functions converges uniformly. So stating this properly then, so if we have a sequence of functions fn defined over the closed interval ab, so we're taking this closed interval ab as our domain for all of the functions in the sequence, and of course these functions are real valued functions, and we're going to take all of these functions in the sequence as being continuous everywhere over the domain, which is the closed interval ab. Then let's call the limit of the sequence of functions. So the limit is going to exist first of all, and we're going to call it f. So the limit as n approaches infinity of our sequence of functions, that's going to be called f. And we're going to assume that it's not just a mere limit, but it's a uniform limit. So this sequence of functions converges uniformly to this limit function f over the domain ab. Then, if it is true that all of these sequences are continuous everywhere over the domain, which is the closed interval ab, you can now conclude that this limit function is also continuous everywhere over the closed interval ab. That statement, that you can conclude that about the limit function, that is what is known as the uniform limit theorem. So I've put that result in red here with a box around it. So it's that if all of these functions in the sequence are continuous everywhere over the closed interval ab, and f is the uniform limit of this sequence of functions, then the uniform limit theorem says that f is also continuous over the closed interval ab. And remember this lovely theorem that if the functions in the sequence are all continuous, then the limit is also continuous. This doesn't hold true if we take away the fact that this limit is a uniform limit. If we go back down just to mere pointwise convergence, then you can find a counterexample, and we've studied that counterexample in previous videos where we've been talking about sequences of functions. So I'll reintroduce it here. So the sequence of functions fnx is equal to 1 over 1 plus nx, defined on the closed interval 0, 1. These are, of course, real valued functions. This is what the picture looks like. So here's the domain. This is supposed to represent the interval 0, 1. And then if we take the first few examples, so if we take n is equal to 1, we get the function 1 over 1 plus x. At x is equal to 0, that's 1, and then as you go along in the domain it goes down, and then at x is equal to 1 it will be equal to a half. And then if you look at the second one in this sequence of functions, we'll have 1 over 1 plus 2x. Again, at x is equal to 0, that starts up at 1, and then as you progress down or along in the domain 0, 1, it will go down to, this time, 1/3, because when you put in 1, you'll get 1 over 1 plus 2 times 1, which is a third. And then it continues on, and these lines are supposed to represent the first 4, if you like. And this continues on forever. And we've discussed in previous videos that the limit of this sequence of functions is this function f, and this is not a uniform limit. We discussed that in the previous video on uniform convergence, but it is the pointwise limit, and it's going to be 1 at x is equal to 0, because every single one of these functions always maps 0 onto 1, so when you evaluate all of these functions at 0, to find the pointwise limit for x is equal to 0, you're just going to get the limit of a sequence of 1s, which is 1. And then for everything else on the interval 0, 1, not including 0, it's going to be 0, because for all non-0 x's here, this bit will play a role, and then as n goes off to infinity, this will always eventually become huge, indefinitely big, and therefore this quotient will go to 0. So this function f is shown in red on the picture, so it's 1 at x is equal to 0, and then it's 0 everywhere else on the interval 0 to 1. And this is the pointwise limit of this sequence of functions. Now, these functions in this sequence, they are all continuous functions everywhere on that closed interval 0, 1, but you can see, of course, that the limit here in red is not a continuous function, it's discontinuous at x is equal to 0. So here is a counterexample for this theorem being true if we take away the uniform limit requirement here. It doesn't hold true, basically, if you take away that. Here's a counterexample. So you do need this to be a uniform limit in order for you to be able to make this conclusion. So this is the first example of how a nice theorem holds true if we have the stronger notion of convergence, of uniform convergence, which doesn't hold true for mere pointwise convergence. So let's now begin the proof of this theorem. So we start with the assumption then that we have this sequence of functions defined on the closed interval AB that are real valued functions that are all continuous everywhere on that closed interval AB. We also start with the assumption that this sequence of functions converges and the limit is f, and this is not just a mere pointwise limit, this is a uniform limit. I've started by drawing a picture. Here we have our domain, the closed interval AB, and the thing that I've actually drawn on here is the uniform limit that we're assuming here, f. And I know I've drawn it as continuous, which is what we're going to try and prove. We will prove that, but allow me to draw the picture as continuous. What I've also drawn on here is this blue tube here. So we know that this limit is a uniform limit, so it therefore obeys the uniform convergence criterion, and that says that for any epsilon greater than 0, you can draw this interval which forms a tube above and below the uniform limit, and there must exist, however small you make it, so I've gone above epsilon by epsilon and below by epsilon for the entire function and plotted this interval going along to form this tube here. And no matter how small you make that epsilon, so we can make it smaller and smaller, so these blue lines will get closer and closer to the red line, there must exist a point in this sequence of functions such that for that function and all the functions beyond it in the sequence, they are contained in this blue tube around the limit f. And we're going to, of course, use this uniform convergence fact and the fact that all of those functions in the sequence are continuous everywhere over the interval AB to show that the limit f must be continuous over AB. So what I'm now going to do is I'm going to take a point in my domain and I'm going to prove that this limit f must be continuous at that point. Now initially I'm going to take a point that is not one of the boundary points, so it's not A or is not B. The boundary points we have to consider separately because there we're only going to be able to deal with one-sided limits and one-sided intervals. So they have to be considered separately. It's no more difficult, we'll just do that later. For now, let's take a point that's actually inside our interval. So x is in the open interval AB, and we want to show that f must be continuous at this x, and I'm not specifying which one it is, so if we show this, we'll have shown it for a general x in that interval. So we'll have done pretty well. We've got most of the interval at that point, proven that the limit is continuous over most of the interval. So forgive me, I am just going to rename this point. I'm going to actually call it x0 rather than x, just to use more conventional notation. Otherwise it would have got a little bit messy with what I'm now going to call this thing here in this limit. So we'll call this point x0 instead, this point that I've chosen in the open interval AB. So in order to show that the function f is continuous at x0, I need to show, by definition, that the limit of the function f of x as x approaches x0, so now you see why I've called this point x0 rather than x, so that I can use this conventional notation here of x. I need to show that this limit as x approaches x0 of f of x is equal to the value of the function evaluated at x0, so f of x0. So that's just the definition of the function f being continuous at x0. So now all I need to do is turn this into the epsilon delta definition. So this limit being this, what I've done here is I've marked that point, and that's f of x0. It means that for all epsilon greater than 0, there must exist a delta greater than 0, such that if you look at this delta interval around x0 in the domain, so the interval x0 minus delta to x0 plus delta, then it is mapped entirely into this epsilon interval around f of x0. So that's what this is supposed to represent up here, the epsilon interval. Now, normally when we do the epsilon delta definition for limits, we would have to exclude off the center point of the interval, so we'd have to take away x0, but of course we don't need to do that here because x0 is trivially going to be always mapped into any one of these epsilon intervals, whatever epsilon you pick greater than 0, because it's being mapped into the center point of all of those intervals. So we don't need to worry about that here because it's the continuity definition rather than the general limit definition, where the limit of the function might be something different to the value of the function. So now what I need to do then is, for a given epsilon, I need to show you how to find such a delta that satisfies this. I need to show you that a delta can always be found using what I know. So I'm going to start by saying let epsilon be greater than 0, and you'll see how this all works out. I am going to now go to the uniform convergence criterion that I know is true, and I'm going to use epsilon over 3 here for these epsilon intervals in blue. So the picture isn't quite accurate here. If this was the epsilon interval, then this blue line would have to be much smaller, so it would have to be really, really close to red. I'm not going to change it because it'll make the picture look difficult because that blue will be so close to the red. But imagine now that I'm drawing this blue tube around the red limit really, really close, so that it is a third the size of this epsilon interval around the red function at this point here. Then, by the uniform convergence criterion, I know that I can go along in this sequence of functions to some f big N such that this f big N of x as a function is always inside this really tight blue tube around the red limit, i.e., writing this out in symbols, that if you look at what fn of x minus the limit f of x is, and you take the modulus of that, it's always going to be less than epsilon over 3 for all x in the domain, so any x you take over that interval ab. So all that's saying is that entirely over this domain, this function, if you look at how far away it is from the limit at any point in the domain, it's less than epsilon over 3, which means that it's inside that tight blue tube. So I've actually changed my picture slightly to make it make more sense. So what I've done, rather than shrinking the blue line closer into the red line, what I've actually done is changed my epsilon interval so that it's more to scale, so that now this epsilon here and this distance from the blue line to the function, the distance from the blue line to the function is supposed to be now a third of the distance from here to here. So it's now supposed to be representing epsilon over 3 better. So now I've also added on here f big N, so I can find this function in my sequence of functions such that it's entirely contained within that blue tube of interval size epsilon over 3 around my limit f. And what I know, of course, about this function is that it's continuous everywhere over the closed interval ab, because that was one of my starting assumptions, that everything in the sequence of functions was continuous over the entire domain. So what I'm now going to do is use the fact that f big N is going to be continuous at x0, and I'm going to say, well, there must exist, therefore, a delta interval around x0 which is entirely mapped into an epsilon interval around fn at x0. So that's what's denoted here in purple. So this is f big N at x0 here. And I'm not going to use epsilon, instead I'm going to use epsilon over 3 again. So I've marked on here, this is supposed to be an epsilon over 3 interval around f big N at x0 there. And I can now find, by the fact that this function is continuous, a delta interval around x0, so an interval from x0 minus delta to x0 plus delta, such that that entire interval is mapped into this interval of radius epsilon over 3 around Fn x0. And my claim is now that I can use that delta interval as the delta interval that will satisfy continuity condition for my limit function f at x0 with interval size the original epsilon, i.e. that this interval here that I've got now, it will be mapped into this epsilon interval in black around f at x0. And let me talk you through why that's the case. So I know that the point f big N at x0 was at most epsilon over 3 away from f at x0. So the maximum distance it could be is on this blue line up here or at the bottom of this blue line down here. I also know that all the points in here, if you look at where they're being mapped onto by f big N, they're going to be at most epsilon over 3 away from f big N at x0. And then finally, I'm not interested in where these points are going to be mapped onto by the function f of big N. I'm actually interested in what they're going to be mapped onto by f. But of course, because f big N is entirely in this blue tube of distance epsilon over 3, I know that these points, where they're being mapped onto by the red line, is going to be at most epsilon over 3 away from where they're being mapped onto by the black line, which is f big N. So that's how I'm able to conclude that the maximum possible distance that, well, actually, they can't actually obtain this distance, but they must be a distance less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, i.e. a distance of less than epsilon away from f of x0. So they must be inside this epsilon interval around f of x0. I'll show you this another way with the triangle inequality. So I can do this by showing a bit of magic manipulation of the triangle inequality. So I've got my delta interval here, which I got from using the continuity of f big N at x0. And I'm going to take a point in that delta interval. And what I want to look at is what is it mapped onto by f, and in particular, how far away is that from what x0 is mapped onto by f, the limit function. So what is f of x minus f of x0, the mod of that? And I want to make sure that this has to be less than epsilon. So I don't know that this has to be less than epsilon. I want to use the way I've constructed this to show that this must be less than epsilon. I can do this with a bit of magic with the triangle inequality. So what I've done here is I've taken this thing and I've made it look more complicated by subtracting things off and then adding them back again, and I've done that overall twice. So this thing that I've got here is actually the same as what I've got here, it just looks more complicated. And let me explain the use of turning it into this more complicated thing. So we're interested in this modulus of this difference between f of x and f of x0. What I've got here, we've still got the modulus, here is f of x, here is minus f of x0, and then all of these things in the middle, they are subtracted, added back on, subtracted, added back on, so they cancel. This cancels with this cancels with this, so this is overall still the same as this. But why have I done this? Because it is easier to compare this and this, this and this, and this and this. In fact, these are the things that I know are all less than epsilon over 3 in modulus. So let's have a look at this in turn. Starting with these two here. So we've got f of x. Remember, x is the point that I've taken in my delta interval here. And then I've got f big N at x. So if we have our point x here, let's say, then here is what f evaluated at x is, and here, above in black, is f big N at x. And if I was just looking at the modulus of the difference between those two, I know that that must be less than epsilon over 3, because I know that f big N has to be in this blue tube around f in red there, because that's the way I found f big N. I used the uniform convergence criterion to say, go along, find me this function f big N such that it's inside this blue tube of radius epsilon over 3 around my limit function f. Now let's look at this next bit that I've got here, f big N evaluated at x minus f big N evaluated at x0. That is also something that if I just had the modulus sign around that bit, I know that that is less than epsilon over 3. Again, because x is in my delta interval, and remember that delta interval was selected using the continuity of f big N. So it was a delta interval that was entirely mapped into the epsilon over 3 interval around f big N evaluated at x0. Therefore, the modulus of the difference between f big N evaluated at x and f big N evaluated at x0 can at most, well, it can't be epsilon over 3, it's strictly less than epsilon over 3. It's a positive number, or it could be 0, non-negative number that is strictly less than epsilon over 3. So that bit I also can curtail. Finally, this bit here, f big N evaluated at x0 minus f evaluated at x0, if I had a modulus sign around that, I again know that that must be less than epsilon over 3, because f big N is inside my blue tube around f. So at x0 also, the modulus of the difference between f big N evaluated at that point x0 and f evaluated at that point x0 must be less than epsilon over 3.